The key thing to remember for an oxidation reduction reaction, and one of the things that I'm going to do is not say oxidation reduction because that's kind of a pain in the butt. I'm going to say redox reactions. Okay, so because that's easier to say. I don't know why we didn't shorthand redox in a way that sounds like oxidation reduction, or why we don't say reduction oxidation, so that makes more sense for redox. Nonetheless, it's what we have. What you're looking at right now is potassium. Potassium metal. It exists like this. I would put a little subscript here that says solid, but the potassium metal contains only potassium atoms. And potassium atoms are all neutral. They have the same number of protons and the same number of electrons, which makes all atoms neutral. But if I take potassium and I put it in water, I get a chemical reaction. And in that chemical reaction, the potassium atoms, which you see here, plus the water, makes potassium hydroxide and hydrogen gas. But let's take a close look at the potassium hydroxide, the base that was made. All potassium ions are soluble in water, which means we have an excess of hydroxide ions in the water. That's why the alkali metals, because alkali means base, when you put an alkali metal like potassium in water, you end up with a basic solution. And that's kind of an interesting fact, but that's not really the whole key idea behind a redox reaction. The key idea is take a look very closely at the potassium atom. It has what we call an oxidation number of 0. An oxidation number, which I'll talk more about in a minute, is crucial in balancing, looking at, figuring out a redox reaction. But this oxidation number of 0 was changed to an oxidation number of +1. What had to happen to go from an oxidation number of 0 to +1? That is the essential question we're going to answer in this video. Please note the next several slides regarding oxidation numbers are not on your packet. Please make sure you take notes on another piece of paper, or if you have room on the sides of your packet, you may take it there. Before we can start doing redox reactions, we need to understand what oxidation numbers really are, because we're going to have to assign different elements oxidation numbers so that we can figure out who gained electrons and who lost electrons. Now, oxidation numbers are simply bookkeeping numbers. Oxidation numbers are, like I said, just a way to keep track of electrons. Oxidation numbers can be positive or negative, but the key thing to remember is these things are not charges. They're not charges. Not charges. They often look like charges. They're often the same as charges, but they're not charges. They're oxidation numbers. Let me give you an example. Take sodium sulfate. Sodium has a charge of +1, and its oxidation number is +1. Oxygen has an oxidation number of -2, and it's the same as its charge. But sulfur has an oxidation number of +6. Clearly, that's not its charge. So, notice, they are not charges. They often look like charges, but they are not charges. There are some oxidation number rules that you do need to know. The first rule is the oxidation number of an element in its free, or rather uncombined, state is 0. So if you take a hunk of aluminum, its oxidation number is 0, which is the same thing as a hunk of aluminum's charge. I understand that, but these aren't charges. They're oxidation numbers. Take a look at tin. What would tin's oxidation number be? 0. Now, I do like to call this the natural rule. And the reason I like to call it the natural rule is if the element is in its natural state, like an uncombined state for aluminum or tin, But the diatomics, think about the diatomics, they naturally exist like that. So its oxidation number is 0. Can you think of another diatomic? Right, so oxygen would have an oxidation number of 0. There's another one that we haven't really covered, and sulfur has a natural state of S8, and so its oxidation number would also be 0. The second rule is the monoatomic rule. Well, I should have probably called it the monoatomic ion rule. So I'm going to go ahead and input the word ion here. Now, the monoatomic ion rule means that if you have mono, one ion, so one atom to one ion, then the oxidation number really is the same as the charge. So sodium has a charge of +1. It also has an oxidation number of +1. Sulfur has a charge of -2. Sulfur all by itself has an oxidation number of -2. So if it's a single ion, not a polyatomic, just one ion, its charge and its oxidation number are the same. This rule I like to call the total rule. It says the sum of all oxidation numbers in a neutral compound is 0. So we already took a look at sodium sulfide and found out that sodium has an oxidation number of +1 and sulfur has an oxidation number of -2. If we add those up, we end up with 0. So the sum of all of the oxidation numbers has to equal 0. 2, I use the 2 because there's 2 here, so that 2 times the oxidation number 1 plus sulfur's oxidation number, add them up, you get a 0. I know, these look like charges, I get that. They're not. The total rule also applies to ions. If I were to take a look at a polyatomic ion like chromate, chromate has a charge of -2. So whatever the oxidation number of chromium is, plus the oxidation number of oxygen, those must add up to -2. This is the column number 1 rule, or you could have called this the alkali metal rule. And it's very similar to the rule we had earlier for extra points. Tell me what rule it is similar to. However, this one says that the oxidation number of an alkali metal is always +1 if it's in a compound. Not a standalone, because remember, if we take a look at potassium as a solid hunk of metal, its oxidation number is 0. But if it's in a compound like potassium phosphide, the oxidation number is +1. Okay, there are oxygen rules. Yeah, more than one rule for oxygen. The first rule is that the oxidation number of oxygen in a compound is always -2. I don't know why I wrote that, so here, -2, just like that, -2. Well, that's a lot like its charge, isn't it? Well, if oxygen's in a compound versus free oxygen, free oxygen in its uncombined state has an oxidation number of 0. But if it's in a compound, then its charge will be -2, which means calcium had to be +2 because we know that the sum of the oxidation numbers has to equal 0. I know, they look like charges. I get that. Trust me, they're not always charges. This is why the oxygen has a plural on the end of its word rules, is because oxygen isn't always just oxygen. Sometimes it's peroxide. And if you're looking at peroxide, then the oxidation number is -1. For example, look at hydrogen peroxide. Now we know hydrogen, being in column 1, and a monoatomic ion means it has to have an oxidation number of +1, which means oxygen has an oxidation number of -1. And we could have figured that out because we know that the sum of the oxidation numbers has to then equal 0. The hydrogen rule states that the oxidation number of hydrogen is usually +1. it sits in the alkali earth metal row, not earth, I said that so wrong. It's in the alkali metal column, and it can behave like a poser as part of that group, which gives it a +1 charge and an oxidation number of +1. So if you take a look at water, we know that water then has to have a +1 oxidation number. However, if the hydrogen is a hydride, then the oxidation state is -1. Take a look at calcium hydride. Well, hydride in this case implies, remember it ends in "ide", so it's an anion. And that means this would have a -1 oxidation number, and there's 2 of them, which means calcium would have to have an oxidation number of +2, which gives it an overall charge of 0. So in this particular compound, hydrogen's acting like an anion, so we call it hydride, which is why its name is calcium hydride. And then we know hydrogen does not have a +1 oxidation number. It has a -1 oxidation number. -1 oxidation number. The last rule we have is the fluorine rule. And the fluorine rule simply states that the oxidation number of fluorine is -1. So if you look at hydrogen fluoride, we know hydrogen is +1. So fluorine has to be then -1. So I'm going to go ahead and write that, -1. And if you look at calcium fluoride, fluoride's oxidation number is -1. We have 2 of them, so calcium's oxidation number has to be +2. Now, unfortunately for you, these rules do not commonly apply to chlorine, bromine, or iodine unless, these guys will always have an oxidation number of -1 unless these guys are hooked up with fluorine or oxygen, and then we'll have to figure out the oxidation numbers. That's what's coming next. Now we are ready to finally use the oxidation numbers in terms of, well, okay, that's not quite true. We just have to figure out the oxidation numbers so we can eventually use the oxidation numbers in redox reactions. Oh, what a pain. Okay, so here we go. Oxygen always, unless it's in its free state, has an oxidation number of -2. So that means this portion of the molecule is worth -14. Strontium, well, it's a monoatomic ion, so its oxidation number is going to be +2. So we know this half of the molecule is +2. Now the problem is, what is the oxidation number on chromium? Well, we know we have 2 chromiums, so we have to have 2. We don't know the oxidation number, so I'm going to call that X equals 0. Now it's simple algebra. 2x minus 12 equals 0, so 2x equals 12, so x equals 6. Therefore, you would write this down as strontium has an oxidation number of +2, chromium has an oxidation number of +6, and oxygen has an oxidation number of -2. Yay, you're done with that one. Pause the video and see if you can come up with the oxidation numbers for copper 2 chloride. Well, let's see. Chlorine, it's funny, chloride has an oxidation number of -1, unless, of course, it is hooked with oxygen or fluorine, which it's not. So it's -1. So I'm going to put that over here. Let's see. Chlorine has an oxidation number of -1. There's 2 of them. This thing has to add to 0. So copper's oxidation number is +2. Pause the video and see if you can come up with the oxidation number on oxygen. Well, if you said the oxidation number on these oxygen atoms is 0, you got it, because oxygen in this case is in its free, natural, uncombined state. Okay, now magnesium chromate. Pause the video and see if you can come up with it. Well, I always start with oxygen because it's always -2 2, unless, of course, we're dealing with peroxide. So 3 times negative 2 is negative 6. This thing has to equal 0. Magnesium, well, that is a monoatomic ion, so its oxidation number is the same as its charge, which means then we have to figure out what carbon is. Don't know carbon? Nope. Well, let's see. Then it becomes simple algebra. X minus 4 equals 0. Therefore, we can write that magnesium has an oxidation number of positive 2. Carbon has an oxidation number of plus 4. And oxygen has an oxidation number of negative 2. What is the oxidation number on silver? Well, if you said silver is equal to 0 because it's in its natural uncombined state, you're right. Good job. Now let's figure out the oxidation number of lead, sulfur, and oxygen. Well, oxygen is always going to be negative 2 unless it's a peroxide, so that means this part of the molecule is negative 6 and it's got to equal 0. Lead is a monoatomic ion, but we don't know it. It's got to be the same as its charge, right? But we got to figure out its charge. Well, if this half of the molecule has a charge of negative 2, then lead has to have an oxidation number of positive 2 because it would be the same as its charge. The problem is we don't know the oxidation number of sulfur, so I'm going to go ahead and use an X for that. Then it's simple algebra. X minus 4 equals 0. Therefore, we can say lead oxidation number, same as its charge, since it's a monoatomic ion, so plus 2. Sulfur then has an oxidation number of plus 4, and oxygen has an oxidation number of negative 2. Try the next one on your own. See what you can do. Well, let's start with oxygen, negative 2, so that part of the molecule is negative 8. Sodium is a monoatomic ion, and it's a alkali earth metal. No, it's not. I lied. It's an alkali metal. So it's a positive 1, but there's 2 of them. So I'm going to write 2, positive 2 over here. But I don't know what carbon is. So 2, because there's 2 of them, times X, and this whole thing has to equal 0. Now we get to do the algebra. So we end up with 2x minus 6 equals 0. 2x equals 6. X then is 3. Now I'm ready to write the oxidation number of sodium is plus 1, of carbon is plus 3, and oxygen negative 2. If you got it, well done. Let's try the last one, carbon dioxide. Well, again, oxygen has an oxidation number of negative 2, but we happen to have 4 of them. So that's negative 4 has to equal 0. So carbon ends up with an oxidation number of plus 4. Good job. So carbon has an oxidation number of plus 4, and oxygen has an oxidation number of negative 2. We are done with this slide. You are absolutely required to do these 4 problems. I expect to see them in class tomorrow and solved. Give it your best shot. Now that you should know how to calculate oxidation numbers, we're ready to start looking at the actual chemical reactions. Take sodium, for example. We know sodium has an oxidation number of 0. Why is it 0? Well, sodium's in its free state. This is how it looks. And when sodium hooks up with chlorine, which is also in its free state with an oxidation number of 0, we end up with a super violent chemical reaction, and we get table salt. Now notice, table salt is an ionic compound, and the oxidation number of sodium is plus 1, and the oxidation number of chlorine is negative 1. How on earth did that happen? Well, somewhere in this violence, there was some electrons that were exchanged. Somebody stole them, somebody took them, and now we end up with this picture. This is a salt. totally could not resist that. In order to write redox reactions, two skills are absolutely essential. The first skill we've already covered, and that's assigning oxidation numbers. That's the first skill you have to be able to do. The second skill you have to be able to do is to write what's called half reactions. So that's where we're starting now, is looking at how on earth do we write a half reaction and what is it? Well, first take a look at this picture. Who is this guy? Well, if you said sodium because it has 11 electrons, you are absolutely right. Well, sodium is going to lose an electron, and we do not use negative signs in chemical reactions. So the loss of an electron is written, okay, I put the word out there, is written as an electron product. It's like you threw it away. So we write the electron as a product when it loses electrons. Well, once it's lost an electron, then it becomes the sodium ion. The electron is just gone. See, it's not there anymore. Where did it go? Well, take a look at chlorine. See, now chlorine's going to gain this electron, so we write it as a positive gain of electron. We write it as, not as a positive, I should have said that, but we write it as a reactant. When you gain an electron, you write it as a reactant, like that. And then when it gains an electron, we end up with the chlorine ion. Now watch, the electron from sodium, right here, is going to be lost here to give the ion. Chlorine is going to gain this electron. Watch the electron at sodium very carefully. Here it goes. Whee! There it goes. It is now given to chlorine. The only change I probably would have made on this is when it moved, I would have disappeared that. But that's all right. The chlorine ion gains the electron that sodium lost. These are two visual examples. Oops, that's not a good place. These two are two good visual examples, this whole bottom part and the whole top part, of what a half reaction looks like. Oh, better erase the ink so you can see my joke better. Oxidation and reduction are the names of the two half reactions. We call one half of the reaction oxidation. We call the other half reaction reduction. Now here's where it gets crazy. Oxidation is the loss of an electron. Reduction, wait for it, is the gain of an electron. Now pause the video and see if you can get your brain wrapped around that. Oxidation is the loss of an electron, and reduction is the gain of an electron. Wait a minute. How on earth can reduction be gain? How on earth? Well, it actually does make perfect sense, but let me explain how and why it makes perfect sense before you start calling me bad names. Well, let's take a look at sodium for a second. Well, we know sodium happens to have 11 protons, and out here there's 11 electrons. And it's not a big deal to you that sodium is going to lose an electron to become a sodium ion. Well, when it loses the electron, it ends up with a +1 charge. So, sodium is going to lose an electron, and it ends up with a +1 charge, because when it loses an electron, it ends up with not with 11, but with 10 electrons. So 11 plus 10 negatives ends up with a +1 charge. Now, where does the electron go? The electron goes from sodium over to chlorine. Well, chlorine had 17 protons, and it had 17 electrons for an overall charge of 0. See, chlorine. But when it gained this electron, and now that it gained the electron, It has 18 electrons. 17 positives and 18 negatives means the charge was reduced. It went from a 0 to a -1. So when you gain an electron, the charge goes down. And I know some of that is pretty mind-boggling, and we'll keep looking at this. But oxidation is loss, reduction is gain. And a really good way to help you remember all of this is an acronym, oil rig. Oil rig, oxidation is loss, reduction is gain. What is losing and what is gaining? Well, what is the essential particle of all chemistry? The fundamental chemistry particle? It is all about the
Now
electron.
that you have figured out how to assign oxidation numbers, you now should know what reduction and oxidation means. What I'm going to do in the next video is show you how to actually balance redox reactions.